So as we look at these examples of aldol reactions, there's two primary things to keep in mind. One is we often have to figure out which carbonyl is going to be our nucleophile, which one's our electrophile. In some cases, that ends up being fairly straightforward because we might be working with one that, one of the compounds can't form an enolate and therefore can't be our nucleophile. But in other cases, like part A, we have to rely on the relative reactivity of the carbonyls that are shown. From there, once we've made that determination, we then want to be able to figure out reliably, what's the product from one of these reactions. And in general, the product that forms is going to have a new double bond and that new double bond is going to form from the enolate carbon to the electrophile carbon. So once we've identified those, the rest becomes straightforward, and we can draw in our new bonds. So part A, again, first question, what's our nucleophile? What's our electrophile? Both of these are compounds that have alpha hydrogens on the carbons that we've highlighted. So then we come down to looking at electrophile strength. And we know that an aldehyde is in general a much better electrophile than a ketone is. And so under that assumption, we can assume that the first compound is our nucleophile with the enolate forming here, and the second compound will be our electrophile with the reaction taking place at this carbon. Remember, we said in this reaction that the product is going to be that we form a new double bond from the enolate carbon. So the carbonyl that started as an enolate, and that piece in many ways doesn't really get changed. And then we're going to draw a new double bond to the enolate carbon. So this is our new double bond. And then our aldehyde, which was a 4-carbon aldehyde, will then get connected on the other side. And we have our product. Trans double bond, almost always favored in these reactions over cis due to the stability of the product. Part 2, we don't actually have to make a determination because we're looking at an aldol of the same compound with itself. So we can draw it out twice. And for this example, I'll even go through the entire mechanism. We know in the first step, we remove an alpha hydrogen using our base. Again, this time we don't have to worry about which one is our nucleophile and which one is our electrophile because they're the same compound. So that gives us our enolate. That enolate will do nucleophilic attack onto a second molecule of cyclohexanone. Which gets us there. Protonation of the oxygen gives us our initial product. And then to finish the reaction, we have our two-step E1CB reaction. So a second alpha proton is removed. We form a new enolate. And then the enolate triggers the elimination by reforming of the carbonyl, and we kick out the leaving group. And you can see that again, we didn't do it just start to finish, but the product again is we formed a new double bond, and we formed that new double bond between the electrophilic carbon of the carbonyl and the alpha carbon of the nucleophile. All right, part C, in this case, we know that the compound on the right has to be our nucleophile. How do we know that? Well, the compound on the left, benzaldehyde, has no alpha hydrogens. There's no alpha hydrogens, can't form an enolate. So our nucleophilic carbon will be this one. Our electrophilic carbon will be the carbonyl of benzaldehyde. And those will form, again, as we've said, a new double bond, giving us our product. And finally, in part D, you could actually go a couple different directions in part D rather. Um, we have two asymmetric ketones. We have LDA, which is a fairly bulky base. It's not reversible. So we're going to form the kinetic or less substituted enolate. So if we form it over here, we do it on the carbon on the right, or on this carbon. Now, just so we can differentiate between those, let's change color. So if we use the 2-butanone as our nucleophile and the cyclic ketone as our electrophile, then we're going to form a new double bond between this enolate carbon and the carbon of the carbonyl. On the other hand, if we use the other carbonyl as our nucleophile, we'll end up with this product. So this is probably a good example of an aldol substitution, or an aldol condensation, where we would very likely get a mixture of products. And we'd get that because both of these are relatively easy to deprotonate. They're both ketones, so they're both good electrophiles. And again, we'd probably get a mixture.